Hello, my name is Luke, and today, allow me to share with you on my final year project, Smart Contract Analysis and Verification. First and foremost, what are smart contracts? Smart contracts are executable code stored inside the blockchain to facilitate, execute, and enforce an agreement between untrustworthy parties without the involvement of a trusted third party. Smart contracts rely on two extremely important properties, being immutable and distributed. In this project, we will specifically be focusing on the Ethereum blockchain and smart contracts written in the Solidity language. While the properties we discuss are meant to keep the Ethereum blockchain effective and secure, platforms built on Solidity smart contracts still carry its fair share of security vulnerabilities. Some of the common security vulnerabilities include the reentrancy attack. During a reentrancy attack, a malicious contract makes use of a fallback function to recursively call back into the vulnerable contract before the first invocation of the function is completed. Next, the integer underflow or overflow attack makes use of unsigned integers, which are vulnerable to integer underflows or overflows, to manipulate the attacker's own balance and could also drain all the ethers in a single transaction. Lastly, the unprotected self-destruct attack makes use of an unprotected self-destruct function in a Solidity contract. If the attacker is incorrectly given access to the self-destruct function, he can destroy the entire Solidity contract and specify a payable address that can receive the funds from the contract after the self-destruct function is called. The first two vulnerabilities, reentrancy attacks and integer underflow or overflow attacks, have been very well documented in recent years, and many security tools and potential fixes have already been developed to help detect and solve these security issues. Therefore, in this project, we will mainly focus and do an in-depth research on the self-destruct function. This code snippet shows an example of a vulnerable self-destruct function. The function is public, thus the function is accessible by other contracts as well and can be called by anyone. To counter this, adding a required statement or an only owner modifier will assist in confirming that only the owner can call the self-destruct function. However, even with such measures put in place, if a smart contract were to incorrectly allow access to unauthorized users, hackers would still be able to take advantage of the self-destruct function to destroy the contract. Thus, developers should consider removing the self-destruct function unless it is really necessary. There are four main reasons as to why developers would choose to include the self-destruct function. Firstly, functionality and setting changes. Secondly, errors in limits of permission. Thirdly, unsafe contracts. And lastly, unmatched ERC20 token. In our project, we are focused on addressing the reason of errors in limits of permission. In certain cases, developers make mistakes by not adding in the necessary permission checks for sensitive functions in the predecessor contracts, thus allowing anyone to execute the sensitive functions. As a result, developers make use of the self-destruct function to create successor contracts that merely add the necessary permission checks to protect the sensitive functions. Therefore, the aim of this project is to help developers avoid making mistakes with regards to a function's limits of permission in the very first place. To do this, we create a tool called Limiters. Limiters is a limits of permission issues detection tool for Solidity smart contracts. It carries out a static analysis on the abstract syntax tree of a Solidity function to detect any potential security issues with the functions of the contract passed. This flowchart summarizes the conditions that Limiters uses to test the functions of the Solidity contract passed. Firstly, we check if the function is inherited from the OpenZeppelin ERC20 contract. As OpenZeppelin is the library which secures the development of smart contracts, the functions inherited from this contract are assumed to follow OpenZeppelin's security guidelines and are categorized as safe. Secondly, we check the visibility modifier of each function. In general, private and internal functions are considered to be safe. Thirdly, we check if the function has changed the state of the contract. If the function does not change the state of the contract, it is deemed to not be a sensitive function and is thus considered to be safe. Fourthly, certain functions mutate the state of the contract as they call an ERC20 function. In such cases, these functions are also assumed to follow OpenZeppelin's security guidelines and are thus categorized as safe as well. Finally, we check if the function is protected by a function modifier. Function modifiers such as only owner are often used to protect sensitive functions. They are able to make changes to the contract state. These functions are categorized as safe as well. Functions that are not categorized as safe by any of these conditions will be categorized as unsafe and may require additional permission checks. This slide shows the software architecture diagram of limiters. Upon input of a solidity contract, the parser generates the corresponding AST for analysis. Following that, we visit each node in the AST, where each node represents a single function in the contract. For each node, we initialize the boolean safe to be false. Next, we check if each condition is met. If any of the conditions are met, we assign safe to be true. Finally, if safe is true, the function is concluded to be safe. Otherwise, the function is concluded to be unsafe. This screenshot shows an example of limiters in action. We tested limiters on a total of 489 solidity functions and only detected 7 false positives, giving us a relatively low false positive rate of only 1.43%. Due to the limitations of static analysis, it is extremely difficult to eliminate all the false positives, as the analysis is done based on a specific set of conditions that we flagged up. Therefore, it is important to note that limiters is not completely foolproof, but is capable of assisting developers in identifying sensitive functions in their smart contracts, which could possibly require appropriate permission checks. By doing so, we are eliminating the need for developers to include the self-destruct function if the reason for including the self-destruct function is to make changes to a function's limits of permission. We have come to the end of this presentation. Please feel free to refer to my FYP report for a more in-depth explanation of the entire project. Thank you.